Yogah Karmasu Kaushalam.
Hello, I am Manan Dholakiya from Indira Gandhi Center for Atomic Research. Today I would be talking about statistical mechanics and its applications to computations. First of all, I would like to thank Professor Dr. Jagdish Joshi, Professor and Director of UGC HRDC of Gujarat University. HRDC of Gujarat University has done a really good job and it has organized first of its kind online refresher course in India in the year 2018-19, which was attended by over 2500 participants. I would also like to thank Professor Aditya M. Vora and Professor P.N. Gajjar, who have organized this time such a nicely organized workshop, and they have been very much cooperative about all the things. I come from Indira Gandhi Center for Atomic Research, which is located in Kalpakkam, Tamil Nadu, and we here developed fast reactors, which comes under second stage of DAE program, Department of Atomic Energies program, for nuclear reactors in India. Today in this talk on statistical mechanics and the related computational methodologies, what I will discuss about is, I would first discuss some basics of statistical mechanics, but I won't go to the formal way it is taught in the books, but I would be just focusing on some of the important points which would be related to our further studies in this talk. Then after discussing these things, I would be giving a short introduction to molecular dynamics simulations, which is a technique which can relate classical mechanics, numerical classical mechanics to and uses statistical mechanics theory to predict about the thermodynamical and physical properties of materials and systems. And then we will study some of the applications of MD and statistical mechanics by study of equilibration of an ideal gas. And then we will study radiation damage and its simulation. So, what is statistical mechanics? In formal definition, it is a mathematical framework that applies statistical methods and probability theory to large assemblies of microscopic entities. One of the peculiar things about statistical mechanics is it does not assume or postulate any natural laws, but explains the macroscopic behavior of nature from the behavior of such ensembles. For example, a gas which is in a container, whichever gas you take, if you know its pressure, volume, then you can know its temperature. This is known as ideal gas law. But it was available phenomenologically much before then when any statistical mechanics was proposed. It was a phenomenological law, and whichever gas you take, if it is an ideal gas approximation, if you know its pressure, volume, you know its temperature. Statistical mechanics was able to give the formulation of this expression by deriving it using the basics of classical mechanics. So it provided a bridge between classical mechanics and thermodynamics. And we should know the stalwarts of statistical mechanics who actually developed the whole field of statistical mechanics. These were James Clerk Maxwell, a brilliant scientist who was equally great in electromagnetism also. And he was one of the ideals of Albert Einstein. Albert Einstein kept a photograph of James Clerk Maxwell in his office. Then comes Gibbs, who had tremendous contribution in statistical mechanics and whose actually the way statistical mechanics is done today has a lot of similarity to the way he derived. The way he derived the ensembles, he proposed the ensembles, it is done the way Gibbs did it. And Ludwig Boltzmann, who made very seminal contributions like S is equal to K log gamma. The entropy could get related to the partition function, and it was a very splendid formula given by Boltzmann. And also, there are myriads of contributions of Boltzmann in the field of statistical mechanics. Now, before going to StatMech, let us just get a short capsule on classical and quantum mechanics. How it is different from statistical mechanics. What is the main difference? In classical and quantum mechanics, in all the kind of mechanics, there is a one standard mathematical approach, and that approach consists of taking two main concepts. The first one is the complete state of the mechanical system at a given time, mathematically encoded as a phase point in classical mechanics or a pure quantum state vector. So, in case of classical mechanics, a system can be completely identified by a single phase point, and this phase space point consists of its position and its momentum. And in case of quantum mechanics, we take the similar kind of state as the state vector. State vector, the ket psi, which is in Dirac notation, it is known as ket psi, has all the information about the quantum mechanical system. Then this state is evolved in time by an equation of motion. For example, in classical mechanics, the equation of motion would be Hamilton's equations of motions, or maybe Lagrangian equations of motion, or Newton's laws. And in the case of quantum mechanics, that would be Schrodinger equation. Using these two concepts, the state at any other time, past or future, can in principle be calculated. And the methodology of classical mechanics is, for example, it can be done in a number of ways. For example, Newton's laws is force is equal to mass into acceleration, m into double derivative of space with respect to time. Then it can also be done in the way action principle. In action principle, what you do is to get different paths. For example, this is time ta to tb and position xa to xb. A particle could have gone through various paths in the phase space. So for every space you define one quantity s, s1, s2. For every path you define one quantity s, which is the kinetic energy minus potential energy at that particular point. So then you call them as s1, s2, s3, all these paths, and you define a Lagrangian, which is kinetic energy minus u, and action is taken by integrating this Lagrangian over dt from ta to dp. And you take something like minima kind of problem, the extrema finding problem, in which whatever the path delta s becomes 0, the variation in action principle becomes 0, that path corresponds to the real path taken by a physical particle. From action principle, you can derive the Lagrangian equations of motion, and of course from there p is equal to del L by del Q dot and p dot is equal to del L by del Q. This is the way you arrive at the equations of motion. And similarly, the Hamiltonian equations of motion can also be obtained. Hamiltonian is kinetic energy plus potential energy, and here dp by dt is equal to minus gradient of Hamiltonian with respect to the generalized coordinate q, and similarly q dot is equal to del h by del p. In quantum mechanics, the methodology is first you find the state vector, and it is then evolved using Schrodinger equation, which in short is iota h cross into del psi by del t is equal to h psi, and the expanded form is minus h cross square by 2m into del square psi plus v of psi into is equal to e psi, where v is the potential energy. However, do these many details matter? We do not find it necessary to know exactly at a microscopic level the simultaneous positions and velocity of each molecule while carrying out processes at the human scale. For example, when performing a chemical reaction. For example, if there is a gas in a container, you do not really need to know each and every atom's position and momentum. What you need to know is, what you actually need to know is what is the total pressure, what is the total temperature, what is the total volume, and with that you can tell about many of the properties of the gas. It is neither important to know every atom's position and velocity macroscopic details, as well as it is not possible also, because even Avogadro number is 6 into 10 to the power 23. It is impossible to know the macroscopic details of all the atoms in a gas container. Statistical mechanics, what it does is it cleverly connects the laws of mechanics, classical mechanics, or maybe in case of quantum statistical mechanics, quantum mechanics, and the practical experience of incomplete knowledge, because we would not be knowing the macroscopic details of all the atoms, by adding some uncertainty about which state the system is in. For example, let us take the case of tossing of a coin. Let us see how details and statistics work in this. So when we toss a coin, we can in principle know which side of the coin is going to come by classical mechanics. For example, while using classical mechanics, you need to know at what was the initial face of the coin, whether it was head or was it tail, how much force you imparted when you tossed the coin, what was the air drag, and what is the gravity, and all those things. With that, it will go up and go down, and you can actually calculate. And you can predict what face of the coin will turn up, whether it would be head or whether it would be tail. But if someone asks you to do calculations of over some 1000 of coins, it will become extremely tedious calculation. But do we require this kind of detail? So there comes statistical mechanics. For example, let us do this experiment. In this case, the first experiment which I am showing, the plot of number of heads from 20 tosses. So we see that there is a chance that out of 20 tosses, the number of heads would be around 10. It would be more sometimes it can be 12, 14, sometimes it can be 20 also, sometimes it can be 0 also. But the probability of a coin to come up as head or tail is 1 by 2. So in statistics also we will find that almost half of the number of trials we will get heads, and almost half it would be tails. So for example, in this case, the histogram is something like this. It is not perfectly Gaussian, but when you increase the number of trials, right now it was only 20 number of tosses. Now you increase it to some 1000 tosses, then it would be almost at 500. So this is 1000 tosses. So at 500 it will peak. So number of heads that would turn out would be almost 500, and number of tails also would be something like this. So instead of doing all the calculations for all the 1000 coins, what a statistical mechanics scientist will do is he will give you a kind of probability. He will tell that out of this many trials, half of the numbers would be heads, and this would be the standard deviation. Statistical mechanics always deals with some certain distribution. It will tell you the mean and the average error about it, which is known as standard deviation. So with this information also you can predict a lot of properties of the systems you are studying. And later, in fact, if you study more into this, that you will see that this is a binomial distribution, which it is for tossing of a coin. It is a binomial distribution, and if you make the number of trials very large, it will go up to Gaussian distribution. And the distributions tending to Gaussian distribution when large number of experiment is done is known as very important law. It is central limit theorem. So we can also study about that in our some later. This is not the point where I can discuss much more about central limit theorem, but it is very important and very interesting theorem to know about. So any random distribution you take, and you take some n number of random variables out of it, independent n number of random variables, you sum them up. The newly obtained random variable, which has obtained from the sum of these independent random variables, would always follow a Gaussian curve. So this is a very strong and very important theorem in the field of statistical theory. how statistical mechanics works. So whereas ordinary mechanics only considers the behavior of a single state, statistical mechanics introduces the statistical ensemble, which is a large collection of virtual independent copies of the system in various states. Then what we do is to take a probability, to know the probability distribution over all the possible states of the system. In classical statistical mechanics, the ensemble is a probability distribution over phase space points, while in quantum mechanics, this becomes a density matrix. Now, let us discuss a computational approach to do classical mechanics and statistical mechanics. We will discuss about molecular dynamics, which is a numerical approach to classical and statistical mechanics. So, what is the basic principle of molecular dynamics? It is we solve classical equations of motion numerically. So, classical equation of motion, the very basic equation of motion is Newton's laws: force is equal to mass into acceleration. So in MD, we solve classical equations of motion numerically, and the obtained results are then correlated with thermodynamics or thermodynamic states using statistical mechanics theories. So the basic methodology of any classical MD simulations is, first you have to provide the initial conditions, the initial positions of Ri at T0. T0 is the initial time, Ri is the initial position of ith atom, and similarly velocity of the ith atom at T0. So initial positions and velocity you have to provide. Then you have to get the forces obtained from there, because potential energy would be known. So forces acting on the ith atom at position Ri would be known. Then solve the equations of motion numerically over a short step delta t. This equation of solving the equations of motion numerically can consist of various algorithms. You can use Runge-Kutta algorithm. Otherwise, some more sophisticated algorithms are like Verlet algorithm, velocity Verlet algorithms. And this short step delta t, time step, is also a very important thing. How much is the time step between for the equations of for integrating the equations of motion is a very important thing, which we will discuss also after a while. Then after solving it, you advance the time from t to t plus delta t, and then calculate the desired physical quantities. And if you have aimed for a total time of simulation as t max, then you say whether if t has gone up to t max, then you calculate the results and finish the MD simulation. And if it has not reached to its maximum time limit of your simulation time, then you have to do all the procedure again and until you reach to T max, the maximum time of your simulation. So this is a basic MD methodology. However, for molecular dynamic simulations to predict statistical results, thermodynamic results, a very strong, very important theorem is ergodic hypothesis. Not a theorem, it is an ergodic hypothesis, which is central to molecular dynamics to give statistical mechanics results. What is ergodic hypothesis? Ergodic hypothesis is time average and ensemble average should be equal. Time average in molecular dynamic simulations, just like in experiments, what we do is time average. Physical property is calculated at a given time, like at some time x tau, it would be calculated. The physical property can be A. So A is a function of that physical property, phase space point is x at time t. Then, like for example in experiments, you would be calculating temperature at every time, and then you would be taking a mean of all the temperatures. Similarly in MD also we take the time average of the property integrated over time divided by the total time. So this is the way we calculate time average. But in statistical mechanics, what we calculate is ensemble averages. We do not do time averages. We take a phase space function, which is partition function, and integrate over it, take a mean, so that that comes as an ensemble average. The main hypothesis is ergodic hypothesis, which says that for MD to predict statistical mechanics results, the long time average should be equal to the ensemble average. So phase space average over partition function should be equal to the time average. This is the main hypothesis on which MD relies. MD relies on ergodic hypothesis. Now, what are the minimum requirements for molecular dynamics simulations? First is, as I said, that molecular dynamics simulations integrates the equations of motion. What are equations of motion? These are force is equal to mass into acceleration. So we know for calculating the Newton's equations of motion, you need to know initial positions and initial velocities. So similarly in molecular dynamics simulations, you need initially the force itself you require. Force is calculated from the potential, which is minus gradient of V. So after knowing the force, you also need to know the positions and velocities. So positions, for example, in case of crystals, you can define as the initial position of the crystal lattice positions of the atoms in a crystal lattice can be considered as the initial positions, and velocities are obtained from Maxwell-Boltzmann distribution for a given temperature. So initial velocities and positions you have to provide, and you also have to provide the interatomic potential. The interatomic potential actually makes the backbone of any molecular dynamics simulation. How it is derived and what is the philosophy of an interatomic potential can be understood from this very simple, very general interatomic potential, which is the Lennard-Jones potential. So, for example, this is VR versus R, potential versus R. Here, number of initially the atoms are very far away. Then there is almost zero force, zero potential. When they come nearby, a dipole-dipole interaction comes into play, which is attractive, minus 1 upon r to the power 6, kind of minus 1 upon r to the power 6. And later, when atoms come very nearby, the poly-repulsion, their electronic shells start overlapping with each other, and this leads to poly-repulsion. This part is repulsive. So that's why the potential has gone like this. So this is Lennard-Jones potential. V of r is equal to 4 epsilon into sigma by r to the power 12 minus sigma by r to the power 6. So this is attractive dipole-dipole interaction term. While this models the repulsive poly repulsion. It is not actually a physically obtained term. It is an easy thing to do. It is an easier thing to take sigma by r to the power 12 to represent, because it is a repulsive potential also. It has to be a higher potential at closed range as compared to sigma by r to the power 6. Then for different kind of materials, you have to get a different kind of potential. For example, in case of ionic compounds, we can take pair potentials. Pair potentials are very good at representing the systems in which electronic shells remain intact. In case of ionic compounds, the electron density is very small. Ions are completely having the electronic charge intact, and the electronic density is very small in between. The ions have filled electron shells and are thus unlikely to change their electron configuration. So they act as charged balls. So they can be very well represented by pair potentials of the kind Coulomb potential, Qi Qj upon Rij, and some short range potential, which can be represented by your Lennard-Jones potential or some other kind of functional form. So pair potentials well represent ionic compounds. Then another kind of potentials are multi-body potentials. For covalent systems and for metallic systems, we talk about multi-body potentials, where not only the interaction between two atoms is important, but the environment also is important. So for example, in metallic systems, we take an embedded atom method potentials in metal, which embedded atom method potentials represent a positive ions embedded in a sea of electrons. So the real material is imagined to be replaced by a gallium, which consists of a homogeneous electronic gas formed by the free electrons of the metal. So in this case, we imagine that, for example, it is sodium. So sodium ions are filled in an electronic sea. So they are having some charged interaction between pair potential interaction between each other. But there is an environmental interaction also, which is something like they are half merged in a sea of electrons. So this is an environmental effect. So this is represented by this total potential is represented by a pair potential term, and an embedding energy, which is something like they are submerged in an electronic sea, negative electronic sea, with an attractive potential for Na plus ions. Then the next step is to calculation of physical quantities using molecular dynamic simulations. So when you know the potential positions and momentum, you can calculate most of the thermodynamic quantities. So for example, potential energy can be calculated like this. This is the expression for kinetic energy. The total energy obviously can be calculated by the sum of potential and kinetic energy. And kinetic energy then can be related to temperature by the well-known law 3 by 2, kinetic energy is equal to 3 by 2 nkt. Then you can also calculate mean square displacement by the current position minus initial position of the, by taking the standard deviation of current position minus initial position. And then mean square displacement, from mean square displacement you can calculate the diffusion coefficient. Then you can also calculate pressure, volume, and other properties like radial distribution function, Van-Debraham parameter, number of defects, etc. Now let us apply our studies, molecular dynamics simulations and statistical mechanics, to study of a gas in a container. In this case, I have taken a gas which is located only in one of the halves. There are two halves, left and right, of a container. But initially we have forced the atoms to be only at the left half of the container. And we want to simulate this condition using molecular dynamics simulation. So what comes out? So first of all, just with this system itself, first we see the importance of the time step in any MD run, which I told about when I was talking about the general methodology of MD simulations. I talked about that delta T time step is very important. It has to be taken judiciously. It should not be very large. It will lead to loss of energy conservation. And then it should not be very small also, because if it is very small, the calculations will become computationally very extensive. So here is an example for this system itself. First we do the time step convergence. So this is total energy versus number of steps, and taken for different curves or for different time steps. Delta T is equal to 0.000125, 0.0025, similarly up to 0.01. We see for time step is equal to 0.01, the energy decreases like this after the when the simulation proceeds. While for other time steps, it still decreases, but for the 0.00125 it decreases very little. It is almost constant. So this time step is good. We should take this kind of a time step. This very large time step is not good for these simulations. So similarly, we have to do all the different tests also. For example, we should do energy convergence, time step, and potential test. All these steps we should do for a good MD result to be obtained by us. Now this is the fraction of atoms, number of atoms in the left side versus total number of atoms of the gas, and we do a simulation how the gas atoms behave. So the fraction of atoms in the left side initially was obviously 1. Number of atoms at the left side were 1. In this system, we took this system, so fraction of atoms at the left side obviously is 1 at the outset, at the initial time. But later, as time proceeds, we see the fraction goes to 0.5, half. It fluctuates a lot. But half means that half of the number of atoms are in the left side and half of them are in the right side. But it fluctuates vigorously around 0.5. So we see that eventually it reaches to 0.5 only. So fraction of atoms in the left side approach 0.5. Both sides, that means, are having equal number of atoms. But we see that this part, fraction is equal to 0.5, exactly 0.5, very small fluctuation around 0.5 has come after a long time. This part is known as equilibration. When the system has completely equilibrated, it will fluctuate very little around its mean. So for the long time simulation, we see that the total number of atoms in the left half and the right half are almost equal, apart from some small fluctuation. We also have to see, if we would have done a very small simulation up to here only, we would not have got the proper equilibrium properties. The system would have been still fluctuating vigorously around the mean, which is 0.5, half in one half and half in another half. So we see we should do a long enough equilibration to obtain proper equilibrium properties. So fraction of atoms in the left side approach 0.5 for long time simulation, and so long time simulation becomes important. So when we see this, what has happened is initially we had taken the configuration at time t is equal to 0, which has equilibrated as almost equally in both the halves. Number of atoms get distributed almost equally in both the sides. And what is the fluctuation in equilibration in MD simulation? So this is different simulations for the same condition. Initially we took all the atoms in the left side and we saw how by time they equilibrate, but these are different simulations. So we see that this is blue versus green, the trajectories are different, they are not similar, but still we see that the main characteristic between them, both of them, which is equivalent, is that they both fluctuate around the mean. Here the total number of atoms were 400 and the number of atoms after equilibration fluctuate only around 200 something, about 220 to maybe 180 they are fluctuating. The trajectories in the two different kind of simulations are different. There is no doubt about that. They cannot be similar. For example, if you had done a series of tossing of coins, you and your friends would have got a different kind of results. Out of 1000 draws, your friend might have got 510 heads and 490 tails, while you would have got some other different numbers. And similarly, the sequence of head and tails would have been different. But the thing which will coincide for both of you is the mean and standard deviation. Both of you would get the similar around, if 1000 were the total number of tosses, so in and around 500 would be the mean, and standard deviation would also be comparable for both of you. So this is very important thing in statistical mechanics, is that the individual trajectories don't matter. What matters is the equilibrium properties, the statistical properties. So for all the trajectories, we only go for the distribution, what is the mean and what is the standard deviation around it. Now, after knowing the importance of the statistical mechanics in MD, let us go to another application. The study of radiation damage in materials. Can we study radiation damage using MD? So this is a typical picture of the dimensional changes in fuel bundles upon exposure of neutron radiation. What happens is in nuclear reactors, the clad materials, the system, all the materials which encompass the fuel materials get heavily irradiated by highly energetic atoms, and that produces a lot of defects and damages the material. So the radiation damage is a process which is very important to be learnt by the whole nuclear industry, so that we can develop better materials. And molecular dynamics actually can help us to understand this process. So let us see how, and for that let us see how this radiation damage process actually starts. How radiation damage starts is, the most primary stage of a radiation damage cascade is displacement cascade, the primary stage of RD. How displacement cascades start is that initially a very highly energetic atom, which from the fuel material, strikes your material, and it knocks off another atom in the matrix, in the target matrix. The atom to which high energy has been imparted is known as primary knock-on atom, pKa, primary knock-on atom, and it gets a very high energy, and in turn it collides with other atoms. So all the atoms get the energy transfer, all the atoms get a lot of energy, and they in turn strike other atoms also, and it becomes a sequence of collisions, and this sequence of collisions is known as displacement cascades. This process is very good to be studied by molecular dynamics, because all this process occurs at atomic length and time scales. MD is actually the best technique to understand displacement cascades. Again, going into some pictorial way to represent displacement cascades is, say there was a crystal lattice of you were having a crystal lattice, a highly energetic atom strike the a crystal lattice atom, it went some way and this atom then collided with other atoms. When it collided with this atom, it created a vacancy over there and the atom went to some other crystal lattice position. So wherever the extra atom has come, that position is known as interstitial. So radiation damage, the displacement cascade produces the number of defects, production of defects occurs. And the most basic defects are the point defects, which are vacancies and interstitials. Vacancy is a vacant position of an atom, and interstitial is an extra atom in the lattice, in the crystal lattice. A vacancy interstitial pair formed by transferring an atom from a substitutial position to an interstitial position, and this pair is known as Frankel defect. So the process is pK strikes the other atoms, and secondary atoms also. First, the primary knock-on atom strikes other atoms, secondary knock-on atoms. These secondary knock-on atoms again will strike other atoms. These would be tertiary knock-on atoms, and so on. This is a sequence of collisions, and there is a minimum displacement energy required for the atoms to become to leave their crystal lattice when a highly energetic atom strikes them. This minimum energy is known as displacement energy, ED, which is the energy required to displace a lattice atom. This is a very popular picture by Brinkman. Before even computer simulations came, he predicted that this should be the way a radiation damage event should happen. So a PK, primary knock-on atom, travels through the crystal lattice like this and creating empty space, the clustering of vacancies actually, and leading to interstitials, the atoms going into some other positions as interstitials in the lattice. So this is a picture imagined by Brinkman, and it was later validated by computer simulations. These are the typical time scales in a radiation damage event. So initially, energy in the 10 to the power minus 18 seconds, the energy transfer from an incident particle occurs, and this creates a primary knock-on atom. Then in 10 to the power minus 13 seconds, the displacement of lattice atoms by the pK occurs, and this is known as displacement cascades. In 10 to the power minus 11 seconds, energy dissipation and spontaneous recombination also happens, and clustering happens. This leads to stable Frankel pairs and interstitials. And at the scale of more than greater than 10 to the power minus 8 seconds, defect reactions by thermal migration occurs. So defect starts agglomerating, and this leads to clustering and defect emission. This is the way it was modeled. The radiation damage was modeled by Kinchin-Pease model. It says that it is an effort to model to predict the number of atoms which would be displaced when a primary knock-on atom of certain energy T strikes a crystal lattice. So it says that up to ED, up to displacement threshold energy, there would be zero number of atoms which would be displaced. Later, ED to 2ED, one atom would be displaced, and later it would be a linear. So this is the kind of model Kinchin-Pease could give. But we are having molecular dynamics simulations at our hand. So can we actually calculate, can we actually see the processes occurring at displacement cascades? So now we try to do this. So as I told that for any MD simulation, we require the lattice positions, initial positions and velocities. So here we are trying to study the displacement cascade using MD. This is a crystal lattice, and here only we will study we will take one of the pK. So for MD simulations, we require a potential simulation box to be designed and proper thermostats. Then these are the details. I would not discuss them in this talk, but you just see that there is a simulation box which is created around the crystal lattice, and we have to define different ensembles. For example, this is macro-canonical or canonical ensembles according to our own requirement of the simulations. And then in this system, we take one atom these are all the atoms are inside in this container. One of the central atom we take as a primary knock-on atom, and to this atom we impart a lot of energy, which displaces other atoms and creates a displacement cascade in the system. And this displacement cascade we study by using MD simulations. So this atom is imparted high energy by us. So it starts colliding with all other atoms and provides a displacement and creates a displacement cascade. So this is an example of point defects in silicon during the implantation of AL clusters. This was a result published by us in Journal of Applied Physics in 2015. Now it comes how to analyze the number of point defects in an MD simulation. So this is one of the ways to analyze the point defects. Point defects are interstitials and vacancies. In this, the defective reference structure is taken, which was the initial configuration of your system, and it is then compared with the defective structure, which has come out after you have performed the displacement cascade. So this is your reference structure, this is your defective structure. This is going to be compared to a reference structure. So around every atom you create an equivalent sphere, and then we take this defective structure and compare it with the reference structure like this. It goes here, and we see that in defective structure there is not an atom in this place, but an equivalent sphere is not having any atom here, and an extra atom is in here. So this portion where there is no atom is known as vacancy, and where the extra atom is there is known as interstitial. So this is how we calculate the point defects in case of MD simulation. We analyze after MD simulation is over. MD simulations could provide very important insights into the mechanism of displacement cascades. So this is the typical number of defects, number of Frankel pairs versus time plot, which showed that initially the number of defects are very less, 0. Then initially they get increased a lot during the ballistic phase. Ballistic phase means that they are just colliding with each other and energy is very high. Later the defects after a peak, they start recombining. So the total number of defects which were initially produced start getting decreased. And they decrease and later they get annealed. They become somewhat constant to a lower number. So initially there was 0, they become very high, but after recombination and annealing, they became quite less, they became 1000. So MD showed that the surviving number of defects are lesser than that predicted by NRT formula based on binary correlation approximation, or even Khinchin-Pease model, which we discussed a bit before, predicts higher number of atoms. MD could give the insight that the number of defects recombine also. This information was not available by the other techniques. This is also an example of cascade. This is the number of atoms which have been displaced. So subcascade branching was seen by Rubia et al. In their MD simulations. Now, after obtaining the number of defects, there is also one way to analyze the topology of the damage or disorder in general. This is an important analysis which is now getting very popular in case of glassy systems also. This is ring analysis. This is a topology based analysis and takes the graph theoretic approach. A graph consists of nodes, which is in this case would be in case of a crystal lattice would be atoms, and edges. In case of crystal it would be bonds. Edges connect two nodes. Ring, which is taken to be primitive, is the shortest closed path which starts from a given node, traverses a continuous path via different edges, and nodes and returns back to the same initial node. And order of a ring is number of nodes present in a ring. So for example, the atoms are the nodes and edges are the bonds. This is one of the rings. The red is this is a closed path. It is a primitive ring because it is the shortest path which starts from A and reaches back to A from here. Similarly, another shortest path from H to H, this can also be taken. Similarly, another ring can be the center ring, which is of having different order because the number of atoms are different in this case. And using this, in case of crystal lattice, we can calculate the number of rings. For example, this is the YTIO system. In case when we were studying Y2TI27 and Y2TIO5 systems, we were having yttria polyhedra connected by oxygen atoms and titanium polyhedra also having oxygen surrounding it. These were the polyhedra. So these were the type of rings which were present in this. This is a yttrium atom, this is a titanium atom. So this is one, and these are the oxygen atoms. Other oxygen atoms I have not shown in this figure. So this is one 4 ring, order 4 ring, because number of atoms are 4. 1, 2, 3, 4. So this 4 ring actually depicted the edge sharing between these two polyhedra. Similarly, this is again the same system, YTIO, but different surroundings of the polyhedra. In this case, this is a different polyhedra which has been connected by 2 titanium polyhedra like this. So in this case, it is a 6 ring because there are 6 number of atoms, 1, 2, 3, 4, 5, 6, and these depict the corner sharing between the polyhedra. So this is a order 6 ring and this is a order 4 ring. So this is a ring in case of YO, TIO. And one of the very interesting result which we could get by studying the topology of disorder was that a melted system can be different from a radiation damage system. In general, when we are doing some general considerations, we would think that any disorder should be a disorder. It should not have the signature of the reasons which caused the disorder. Like melted system is also a disordered system, and a radiation damage system is also a disordered system. What should be the difference between them? They should be completely alike. But we found that if we do some ordinary analysis, for example, radial distribution function kind of analysis, the heated sample, the melted system, and the radiation damage cascade peak system look completely similar. So our basic intuition that a disordered system should not have any signature of the reason of its disorder gets satisfied because they look similar. But when we do a ring analysis, topology kind of analysis, where we analyze the order of rings, we find that here is a ring order, here is the total number of rings, 4 order, 6 order, 8 order, and the total number of rings corresponding to that. We found that the heated sample, the melted system, which is represented by blue curve, is having a very different topology from the radiation damage system, which is depicted by cascade peak, the system which was frozen when the cascade was at its peak. And both these systems are having a very different topology from their crystalline counterpart. But the point to be emphasized is that the radiation damage system is very different than the heated sample, the melted system. And this difference is discerned by only ring analysis, the topology based analysis, while that difference is not visible in some other analysis, for example, radial distribution function analysis. So RDF of a melted and cascade peak samples are similar, but topology is quite different. This means a radiation damage system can have a very different topology from a melted system, and this difference can be effectively discerned by ring analysis. Similarly, we studied the role played by atomic interactions, and we studied how much the energy difference comes when the systems are disordered. This also are done using molecular statics, which is we are not doing dynamical calculations. We are just for different configurations we are calculating the total energy with respect to which is calculated by the interatomic potential. So here what we do is we change the configuration, and for every configuration we calculate the total energy. So here in this curve we have compared the energy change when the polyhedra are rotated by a certain angle, theta degrees, And in this case, Y2TI5, Y2TI27 and Y2O3 have been compared. And here by this comparison, we found, applying the Zakarian criteria, that the system which gets higher energy change upon distortion would be very less amorphizable. So we found that these systems get a very high energy change, so they should be not readily amorphizable. They should resist any kind of disorder in them. While SiO2, silicon dioxide, which is a readily amorphizable system which can be easily disordered, gets a very less energy change up to when the distortion in their polyhedra was up to 45 degree. So these are the ways we should analyze radiation damage systems. So with this, I would like to finish this talk, and you can contact me in, these are my email IDs, manan@igka.gov.in, and this is my Gmail ID. Thank you.